and pictures. Okay, so third lecture. Questions from yesterday. Yesterday, hands-on. Yes. Oh, yeah. So you should expect two things. First, the rates. I didn't ask you, but you can also do the plots with the rates. You should have like higher rates with like a larger spread. I think the reason is going to be clear now. And also you can see changes in the Mach spectrum. So this is like to convey the thing that metallicity matters, especially how we model metallicity, which is also the topic of today. Well, it depends on the population synthesis that was used. In your case, you don't see like a striking difference. But I can upload other catalogs where you can see like this difference actually having like major effect. Okay, so lecture 3 it will be basically so we are going to see what is in detail, like in deeper details, what is multi-messenger astrophysics, and this is connected to host galaxies. So we are going to learn how we model host galaxies and basically the impact that like modeling host galaxies has on other fields, for example, cosmology. So we are going to see like how we can combine gravitational waves and cosmology in terms of parameter estimation, for example, of the cosmological constant. So when you have a multi-messenger event, what you are observing is the gravitational wave event, for example, GW17-0817, the merger of two neutron stars, and a bunch of electromagnetic emission, for example, a GRB, like a short GRB. What we are, and this is good, but what we are looking for is the kilonova. So if you look in this picture here on the right, you have the GRB central engine, which is the merger of the two neutron stars. And right after, you have the kilonova, which is an isotropic emission of electromagnetic waves. The prompt emission of the GRB, which is highly instead polarized with respect to kilonova, which is highly isotropic. So this emission comes from radioactive decay of heavy elements. And is particularly important because like when you observe a kilonova, you can put constraints on many areas of physics. And what I mean is this. You can model the luminosity peak of the kilonova with the equation on the top. I'm not going into the details of the equation, but this depends on the ejected mass. So when the two neutron stars collide, you have ejected mass, on the velocity of this ejected mass, and this is highly related with astrophysics. For example, this depends, for example, on the equation of state of neutron stars. The opacity during the kilonova emission is related with atomic physics, and the radioactive heating rate is connected with the nuclear physics. So the message here is when we observe a kilonova, we have like a full picture of at least 3 areas that are connected, of course, but like two areas of physics just in one glance. So we want kilonova emission. However, there are problems, of course. What I'm showing here is the light curve of kilonova. These are the lines, these lines here. So this is light curve as function of time. So absolute magnitude as a function of time. The light curves are the blue and red lines. The green lines instead are the afterglow emission after the GRB. The 3 panels are 3 different inclination angle, 0.1, Why? If I do that. Okay, 0.1, 5 degrees, 10 degrees, and 20 degrees. This is the inclination angle between the usual inclination angle that you see also with GW fixed, for example. The inclination angle between the angular momentum of the binary and the line of sight. So if you have your binary neutron star, so your GRB emission, so if you want to see the GRB emission, you must have like a very low inclination angle. Basically, you need to, oh my God. you need to have like almost zero inclination angle. So you must look at the binary face on to see the GRB. And the GRB, the problem is that outshine the kilonova emission because you see, trivially, the magnitude of the GRB is above the kilonova emission. To actually appreciate the kilonova emission, you need to go to a higher inclination angle, like 20 degrees. So you see that the kilonova is on top of the afterglow emission. The problem is the probability to get the GRB with such inclination angle is lower. So what I want to say is that if you want to see a kilonova, you need gravitational waves. Otherwise, it's very difficult to characterize the kilonova emission. I hope I convinced you. So how we observe kilonova? We need low latency. Low latency means that we have the gravitational wave detection, and we want to point our telescope as soon as possible where the gravitational wave emission is coming from. And we need to do that as fast as possible. This is the meaning of low latency. This is how it works. So in a time span of 30 minutes, we have our detectors with automatic searches running, for example, fast parameter estimation that provide us the sky localization, just the sky localization, not the full parameter estimation. No masses, no tidal deformability, just the sky localization. We have human validation. Of course, machines can be wrong, so we want to assess that what is coming from the detector is at least good. And then we have all over the globe a bunch of different electromagnetic facilities. So we want them to be spread all over the globe, because if you have like your gravitational waves, so you need always to have like at least one telescope during the night. We have telescope, of course, on Earth, but also space probes. For example, the Fermi that detected the GRB emission from GW17 1817. And we want human validation. We just don't point telescope randomly, because these are also very fancy telescopes that cost a lot of money. So observing time costs a lot of money, so we want to be sure when we point our telescopes. Okay, so, but we need a low sky localization. Otherwise, it would be that we need to point basically whatever in the sky, so we need to train sky localization. And now I want to tell you how it works, sky localization. So when a detector measures the delta L over L, the displacement, oh my God. It works so nice. Okay, so the detector measures the displacement. Oh my God. Sorry. So the detector measures the waveform that the detector measures is a combination of the so-called antenna pattern, which are the functions called f in the first equation, and you have like one antenna pattern for each polarization of the gravitational wave. So a gravitational wave detector is an all-sky monitor with varied sensitivity. The usual product that is proposed is this one, like in the bottom, where you have like the some square, like the square root of the two antenna pattern polarization, where basically you see the antenna pattern going like into the so the detector is placed exactly in the middle of the thing. Those are called blind spots. So another way to see the antenna pattern, you can project the antenna pattern on Earth. This is the plot that you see on the right. This is the antenna pattern for LIGO Livingston, so that one in Washington State. You see that the antenna pattern is maximum where basically on the top of the detector and exactly on the opposite direction. And you have like blind spots where the detector is, okay, so no fancy pointer for today. Okay. So the message I want to convey here is that the detector has varying sensitivity, so it's not completely, so it doesn't see like a sky with the same sensitivity, and it doesn't have directional sensitivity. So to solve this, we need triangulation. So we need, like the best option would be like to have like an infinite number of the detectors, but at least to localize a source, we need 3 detectors. The triangulation works exactly as it works, for example, for GPS. What you're measuring is a time difference in the difference in the arrival time of the gravitational waves. This is represented in the plot on the left. So when you have 2 detectors, what you're defining is an annulus, which is the plot in the middle. So if you want to localize the source, you need, as I said, 3 detectors. Like each couple of detectors has an annulus, and where they cross, that is your sky localization. You can see how it works in this plot on the right, where you have like the 4 functioning detectors, the LIGO, Virgo, Kagra. And so this gives you the direction where the gravitational wave is coming, but it actually provides you like an area, the so-called sky localization area, which is proportional to the SNR to the 2. So this means the SNR is connected with the antenna pattern that I showed you before. So it means that if you want to have like a good sky localization, you need 3 detectors and like a good SNR, at least in the 3 detectors. Or, as happened with GW17 or 817, what actually shrank down the sky localization for that binary neutron star, it was that it was in the blind spot of Virgo. So the other 2 detectors were actually observing the neutron star. Virgo wasn't observing, so that it really had to direct to shrink the sky localization. And this is what I mean. Sky localization has a scale of 5 degrees, which is fairly good for a gravitational wave. And that actually was the striking effect that allowed us to see the host galaxy. So the host galaxy of GW17 or S17 is well localized. I mean, we know, we know dubs what is the host galaxy, which is the plot that you see here on the right. The galaxy is called NGC 4993. And you see that like a little white circle that is circling something. That is the kilonov emission from GW17 or 817. So we can characterize those galaxies. It's a S0 galaxy, means like an elliptical galaxy, quite massive, 10 to the 10 solar massive, and quite passive. It's not star forming. Like star forming is almost quenched. When we identify the host galaxy, we can identify the redshift like with a super good precision. This galaxy is quite close, so we have like redshift at the 6th decimal digit. And when we have those galaxies, we can also think about, what we can do is to connect the properties of the BNS with the property of the host galaxy. So I told you, massive, passive, but also we saw that this kilonova here doesn't show like a natal kick, or the natal kick is very, very, very small. And there are no globular cluster or young star cluster in the vicinity of that that galaxy. I mean, in the vicinity of the kilonova. So this, so what we are doing now for the last hour, basically, is to connect the properties of host galaxies with the property of compact object mergers, and we are going to see how we model them. So it is a challenge, though, because we are interfacing physics at completely different scales. So you can think like the scale of a compact object merger is the Schwarzschild radius, basically. But you want to interface physics happening at this scale, what is happening at galaxy, a cosmological scale. So it's not easy. A potential solution comes from galaxy catalogs. So we have cosmological simulations, and what we can do is to use those galaxy catalogs and inject in those galaxy catalogs for example, catalogs from population synthesis simulation. Now I'm going to explain you what I mean. There are questions so far? Okay. So in this plot here, you have our universe, starting from the Big Bang up to now. The blue box represent like the redshift horizon of a current gravitational wave detector, so where we can actually see so far. So what we want to do is to take galaxies from cosmological simulations. For example, here, let's focus on a galaxies forming at high redshift, which is like star forming, an early type galaxy, like an early type star forming galaxies. And what we want to do is to inject in these galaxies like a number of binaries, starting from like massive stellar evolution, so the things that we saw yesterday, up to the formation of the two compact objects. We also saw that when you form the two compact objects, you have a delay time between the formation and the merger. So in this sense, we are linking properties of compact object with the property of the galaxy. Because those compact objects can merge, for example, if the delay time is sufficiently long, in a late type passive galaxy, exactly the galaxy that we observe with GW17 or 817. And of course, there is also the merger of the two neutron stars producing gravitational wave. This is like one scenario. We can have like another scenario where we inject our binaries in star-forming galaxies. The delay time is short, and they merge in star-forming galaxies. Of course, we cannot observe this scenario with current gravitational wave detectors, but is a possibility with future detectors. Is it clear how we do? Okay. Okay, once you model host galaxies, what you can do is to rank them. What you can do is to evaluate a probability, the probability that a given galaxy hosts the observed gravitational wave. So you want to evaluate this probability. One way to do that is to multiply those two probabilities. Let me be specific. So P log is the probability that the galaxy can be the host of a gravitational wave observation given the sky localization. For example, if it sits in the like in the 20% credible interval of the sky localization, it has a higher probability of a galaxy that is far away from this 20%. So you can, we can do that because up to a certain redshift, we have complete galaxy catalogs. We almost know all the galaxies that are sitting, close by. So we can use these galaxy catalogs to rank to rank the galaxies based on the sky localization. So this probability here basically takes in account the parameter estimation coming from a gravitational wave. So if the sky localization is larger, of course, you have more galaxies with lower probability. If the sky localization is smaller, you have few galaxies with higher probability. This probability here, instead, basically comes from simulations. So when we plant our catalogs of compact object mergers coming from population synthesis with cosmological simulations. And here I put in the results that we can get from this cosmological simulation. How we evaluate this is we count all the number of all mergers that we have in a given bin of stellar mass and star formation rate, divided by the total number of galaxies that we can see in that same bin. Can you see like a strong correlation in this plot? If you see just this plot, where do you expect to see like your BNS merger? If something is not clear, just ask. I can repeat. Massive and star forming, yes. Your colleague said massive and star forming because like he was looking at the yellow bins where you have higher probability to find galaxies. Do you know why? Do you have a guess? It is like that. So why do we expect in massive galaxies to see BNS mergers? It is as simple as that. If I can correct you, like massive galaxies tend to have also like higher star formation rate. Because you can have like a massive galaxy but with low star formation rate. Can you repeat it again? Sorry. Sure. Yes, sir.
Yeah. So just looking at mass is not. No, it's just a commentary about that. So yeah. Just looking into mass is not enough. That is what I'm basically commenting in what you were saying to him. Yeah.
Comment over comment.
Yeah.
Okay. So yeah, basically massive galaxies tend to have like higher star formation, so like a higher probability to form new massive stars that can lead you to the formation of BNS.
You were saying that when we have more masses, then we have higher star formation, but elliptical galaxies have higher mass, and the population of stars are old, so the star formation stopped. So
that's
right?
That's the one of the things that we want to explain when we want to model host galaxies. So for example, GW1700817, the multi-messenger event, was found in a elliptical and passive galaxy. So we need to explain why we have that BNS in that galaxy. One simple explanation is from this plot here that it was formed in a star-forming galaxy, but the delay time was so long that the galaxy in which was formed had the time to evolve in a passive galaxy. So this is like 101 explanation. Unfortunately, we do not have statistics. We have just one host galaxies. Okay, so that's that's the point. Questions, comment? Okay. So we can, if we model host galaxy, we can also rank them. For example, tomorrow we will have another, I don't know, BNS merger, observing gravitational waves. We have like, in the sky localization, we have a bunch of galaxies. We cannot observe all of them in less than 30 minutes, of course. We need to choose, we need to rank them. We can use this type of simulations to rank the galaxies and to point to the, hopefully, most probable or most likely galaxy that contain also the kilonova, the multi-messenger emission. Okay, problem. Do you trust cosmological simulations? I mean, if you don't have anything better, of course you trust cosmological simulation. But yeah, people, when you talk about cosmological simulation, they are like, you know, a bit sketchy. Yes, they work, but sometimes the prediction they have is not compatible with what we observe. So there are uncertainties. There are uncertainty in the cosmological simulation part, and there are uncertainty in the population synthesis part, in how we model black holes. Just to give you an example, the alpha common envelope that we saw yesterday, it's a free parameter. We don't know the value of this parameter. So we want to take into account uncertainties, especially when, in the case if we want to rank, we want to evaluate the uncertainties on the ranking, for example. Problem is that you do that with cosmological simulation, it's going to take time because cosmological simulation are like huge. You need to follow the evolution of billions of stellar particles. It is like an art place to explore the parameter space. So this is why I would like to talk about galaxy rate, which is a code that I developed a couple of years ago, that allowed you to, with some approximation, of course, but allows you to actually explore the parameter space and look at the key physical properties that are shaping the host galaxy properties. So what matters more, like the stellar mass, the star formation rate, or metallicity. So from now on, I'm going to explain you how galaxy rate works and how it can be like a nice tool to explore this parameter space. Questions so far? I don't think so. Okay, so the first thing that we need to take into account is the galaxy stellar mass function. So we know galaxies. So as the initial mass function, for example, we know the mass of galaxies is distributed. So we can evaluate a distribution of the mass of galaxies. So what I'm plotting here is the galaxy stellar mass function of star-forming galaxies, the panel in the top, the galaxy stellar mass function of passive galaxy in the middle, and the ratio between these two plots. Different colors are different redshifts. So one thing that we can already observe is something that we already discussed. For example, if you take redshift 5, so the green dashed line, and you look at this galaxy stellar mass function of passive galaxies, so I'm talking about, this line here. If you look at this galaxy stellar mass function, this is already telling you that you have less passive galaxies at high redshift. So this is a very important information. The number of passive galaxies, galaxies that get hosted, for example, GW17 or 817, is increasing with redshift. So in galaxy ray, what we want to do is to consider both these galaxy stellar mass functions, the stellar mass function of star forming and passive galaxies. Okay, the main sequence. Why massive galaxies tend to have like higher star formation rate? This is explained by the star formation rate main sequence. You might ask yourself if I was on drug when I did this simple sketch. Yes, I was probably. So here I'm just plotting the equation that you see above. What I'm doing here. This is the distribution of star formation rate at fixed stellar mass. The stellar mass information comes from the galaxy stellar mass function at fixed redshift. So you have two bumps. Like a major bump here is this major bump here is the main sequence. So most of your galaxies tend to sit in this main sequence, where you have an average and where you have a spread. Then you have like a little bump. This is the starburst galaxies, starburst galaxy main sequence. So galaxies that sit above the main sequence that have very high star formation rate. The main sequence can be deducted by observations. So what we do in galaxy rate is to take into account different observations, and we want to take into account also different observation of the main sequence, because this is an effect on our results. This is how the main sequence looks at different redshift and different masses. If you combine the equation of the slide before. So what you can see here is that at high redshift, so redshift 5 again, you see that on average, galaxies were more star forming. As you approach local universe, you see that on average, galaxies tend to be less star forming. So the main sequence is actually, in this sense, the main sequence trace the star formation rate of each given galaxy. You can combine things together, and you can calculate the star formation rate. Do you remember the plot that I showed you yesterday of Cosmo rate? Okay. So Cosmo rate includes this star formation rate, the MF17, the dashed red line, this one, which is fairly consistent with observations, which are, of course, these dots here. The star formation rate of the Eagle cosmological simulation is the black line. This is like one of the examples of the mismatch I was talking about before between cosmological simulation and observations. This blue line here, S14 and B18, is the star formation rate, the total star formation rate density that you can get with two different main sequences. You have like almost 1 order of magnitude at the peak of the star formation rate with two different main sequences. And they fairly agree in the local universe. So in this sense, with galaxy rate, we can explore uncertainties. So both models, S14 and B18, are observed model, of course, on different data, with also in B18 4 years later than S14. So in this sense, we want to take into account uncertainties. Do you have questions? Is it clear? Did I lost you completely? No, kind of. So if you model Ghost Galaxy with the Eagle cosmological simulation, for example, with the Eagle, you are forced to stay with that cosmological simulation. You cannot change the star formation rate, the main sequence, the galaxy's mass function. With Galaxy Ray, you can do that. Okay, do you remember metallicity impact on compact object formation? We discussed it a lot. Yesterday, I showed you that metallicity has basically sets the maximum mass of black holes. But it also has another effect. This is the merger efficiency. So what I'm plotting here is basically given population synthesis run with an initial total mass, like for example, we want to evolve, I don't know, 100 million binaries. This corresponds to a total initial mass. Basically, these 100 million binaries are sampled from the IMF, the initial mass function. Basically, here we are plotting, given that 100 million binaries, how many mergers we have at the end of the simulation. This is the meaning of the merger efficiency, this value here. So if we focus on BHNS or BBHs, you see that at low metallicities, from 10 to the minus 4 and 10 to the minus 3, you have almost like high and constant merger efficiency. So at this metallicity, your massive star efficiently produce black holes that are able to merge. If you approach the solar metallicity and metal-rich stars, the number of black holes mergers plunges down. So if we model host galaxies, we need to take into account metallicity. As yesterday, when we were using Cosmo rate, we need to take into account the metallicity distribution. We need to do also that with galaxies. just to be extra clear, if you have like a black hole forming like in a low metallicity galaxy, you have more chances that that black hole is going to merge with respect to a high metallicity galaxy. This is as simple as that. This sketch, I think, combines what I just said, basically. So if you look at the total star formation rate with the black line, you know that at low redshift, at high redshift, you have the majority of galaxies at low metallicity. This is going to be clear. Oh, sure. Okay, thank you for that. Thank you for that. I completely forgot to comment this. So we see that with BNS, the merger efficiency tend to be almost constant across metallicity, but we have different huge differences if we change the value of the alpha common envelope. The reason is that the star producing BNS are less massive than those producing BBHs. This is clear. So stars that are producing BBHs tend to lose a lot of mass due to stellar winds because of the equation I showed you yesterday. That equation doesn't take into account the initial mass of the star. So basically, with BNS, you're losing you're losing basically less mass due to stellar winds because the initial mass of the star is smaller. But you have like a huge effect on the alpha common envelope. So basically, with BNS, we will expect like a less impact from metallicity. Okay, so I was discussing this plot. So at high redshift, you expect the universe is producing stars with a low metallicity. In the low redshift universe, you're expecting the universe to produce stars with a high metallicity. And you need to take into account this with the evolution of massive star and binaries. So we want to couple these two words. And we expect that the population of gravitational, the final population of gravitational wave sources have different characteristics or different, for example, host galaxies if they are formed in the high redshift universe and the low redshift universe because of the effect of metallicity. And this is the reason why we expect less low metallicity galaxy in the at high redshift. So like another observed fact is the metallicity distribution. So what I'm plotting here is the so-called fundamental metallicity relation and the mass metallicity relation. So these are so-called, so these are two relations that are observed. Basically what happens is that the fundamental metallicity relation defines a plane basically between mass of the galaxy and the star formation rate of the galaxy. And the output is the metallicity. So what you have is that the metallicity distribution doesn't change a lot as you go as you change redshift. So from redshift 0 to redshift 5, you see that the FMR is basically predicting you galaxy with almost the same metallicity. If you instead look at the mass metallicity relation, which is simply a relation between the mass and the metallicity of galaxies, the picture is different. So if you go, for example, redshift 5, you get the mass metallicity relation is predicting galaxy with order of magnitude less metal content. These are observed distributions. So again, with cosmological simulation, you cannot take into account of the fact that we don't know how our universe is producing metals in galaxies, basically. With galaxy ray, we can include this uncertainty. We can either choose one or the other relation and see the difference. Here I am lighting, of course, the fact that at low mass galaxies, you tend to have like lower metallicity. So if you compare this number here to that of the merger efficiency of before, you see that these low mass galaxies tend to form with low metallicity at any given redshift. And so you expect that BBHs are going to merge more efficiently in these type of galaxies. You can combine everything together. So before I was showing you the star formation rate density as function of redshift. Here I'm adding a new variable, the metallicity. So in this plot you see color-coded is the star formation rate in that bin. And the bins are defined as in the y-axis as metallicity and in the x-axis as redshift. So you can already see if you choose the mass metallicity relation or the fundamental metallicity relation, you have completely different metallicity distribution. You get to see. Do you have questions?
So just so that I understand correctly, these different metallicity relations are like different models that you can pick?
So these metallicity relations come from observations. Of course, in the local universe where we have a lot of observation, they match. You can see that basically if you fix at redshift 0, basically you don't have like a difference between the two distributions. Of course, when you go like at higher redshift, where you also need to take in account, you know, higher uncertainties. So they come basically from observations. So when we want to model a host galaxy, what we need to look at is this distribution here. For example, here I'm also plotting the same quantity that you get with Cosmorate. So yesterday you were running this this hands-on section with exactly this this setup here, where you have the S20 model, which is the linear model that you were putting on your parameters file. So with Cosmorate, you can increase the spread of the distribution. So you're gonna have like a larger metallicities, like a larger support to both higher and lower metallicity. But this that you see in these 4 panels here is what you should trust more, because this metallicity distribution comes from taking account like properties of galaxies. So the purple line that I'm plotting here, this is setting the maximum of that distribution. So if you see that if you take into account the mass metallicity relation, you're going to predict like lower metallicities, and if you take the fundamental metallicity relation, the maximum of that distribution is going to be almost constant at higher redshift. So in these 2 columns, instead what I'm changing is the main sequence, S14, B18. And you see that there are also differences, for example, like in these long tails between the 2 different main sequence. So this is just to, what we did here was to basically propagate the uncertainties that we have on galaxy observations into this quantity that can be, I think, can be understood better, especially if you compare it with what you get with Cosmorate. Questions? Okay, so now I want to look at how Cosmorate actually works. what I just described. So we have what we need to do in Cosmoray. We need to define the formation galaxies, and we sample the formation galaxies from the observational scalar relations that I just showed you. So what we do is we need to create a population of formation galaxies. So we sample one galaxy, so we fix the redshift, and we sample, for example, let's take redshift 5. We sample like a number of galaxies from the galaxy stellar mass function. So in this way, we know the mass of the galaxy. We sample the star formation rate of the galaxy from the star formation rate main sequence. And finally, we sample the metallicity, either from the fundamental metallicity relation or the mass metallicity relation. So we will have like a catalogs of formation galaxies with these three different properties. These are the minimum amount of properties that define your galaxy. And similarly to cosmological simulation, we inject catalogs of compact objects. These come from, for example, from population synthesis. Here I'm showing you the delay time of a population of BBHs. So basically what we know are the properties of the formation galaxy. Then we inject the catalogs of compact objects, and these catalogs contain the information on delay time. So what we know is when these compact objects are going to merge. In this plot here, I'm showing the effect of the common envelope on the delay time distribution. So what you see is that with alpha equal to 1, you have like a distribution picked at low delay times. With alpha equal to 5, you have like larger support for longer delay time distribution. So in this sense, we are coupling properties of host galaxies with the properties of compact objects, with the properties of the population of compact objects. Finally, we need to take the properties of the host galaxies. To do that, we are going to use cosmological simulations. I just told you that cosmological simulations are bad, but no, we are going to use them. How we are going to do that? So basically, here I'm showing a merger tree. Basically, what a merger tree contains is the entire assembly history of a given galaxy. For example, you take this is the merger tree of this given galaxy here. Color code is the mass. And on the y-axis, you have redshift. So if you look at this galaxy in the local universe, a massive galaxy in the local universe, this galaxy is made up by the mergers of all these galaxies along the history of the universe. This is something that you can track with a cosmological simulation. This is a merger tree. Of course, the galaxy at higher redshift tend to be like less massive, and this is something that we can also see in the galaxy stellar mass function. So if you go back and you see the galaxy stellar mass function, you see that you have higher support for low mass galaxies. So basically, what we want to do here is to couple the information that we have in cosmological simulation with a population of galaxies that comes from observations. So this is the effort that we are trying to do. However, I cannot use directly the merger trees because the code would be like super slow, and we want a fast code that allows us to explore the parameter space. So what I'm doing from all the merger trees of a given cosmological simulation is to evaluate this conditional probability. So let me explain what it is. Basically, you have the conditional probability is plotted here, for example. So you have the mass of the host galaxy, so the star formation rate of the host galaxy and the mass of the host galaxies. Color code is the probability. So what I'm plotting here is this probability here, conditioned on these properties. So we are conditioning on the mass of the forming galaxies, the star formation rate of the forming galaxies, the redshift of the forming galaxies, and the redshift where the compact objects merge. So the idea is to sample the property of the host galaxy based on this conditional probability. Let me be clearer. So you have, for example, let's take this galaxy that formed a redshift 2 and merges in the local universe. The initial properties of the initial mass is 10 to the 7, and the initial star formation rate is 10 to the minus 3. This is in log. This is the position of the formation galaxies in this plane. So if you, this is telling you, if you inject in this galaxy a compact object that forms a redshift 2 and merges a redshift 0, the final host galaxies is within this space, and the probability it is not uniform, but you have a probability that comes from the merger trees. And you can see how it works if, for example, you change the mass of the forming galaxies and the mass of the star and the star formation rate. We are fixing the formation redshift and the merger redshift. You see this is how it works. So trivially, the host galaxy cannot be like smaller than the formation galaxy. Again, here, almost. Again, here, if you have like this is the formation galaxy, and the host galaxy is sitting in this plane with this probability. Let me be extra clear. So what we do is this: we have our universe at zeta form. So this is the universe at the formation redshift, and our universe at the merger redshift. So these two universes speak because we inject compact objects here, and they merge here. So the connection comes from the delay time, basically, when the compact object forms and when the compact object merges. So what we do is we sample the host galaxy from the conditional probability. For example, this formation galaxies is connected with these host galaxies, and this connection is proportional to the probability. It can happen that you have that multiple formation galaxies, for example, these two, are connected with the same host galaxies. So what you do is that the number of total mergers that you have in these galaxies is summed. So in this summation process, what we are taking account is basically the merger trees. So we know that galaxies can merge together to form like a new host galaxies. You have questions? I wouldn't be surprised. I mean, it's quite. Do you have questions? Okay. Results. After all this effort in developing this, we can actually look at the stellar mass of the host galaxies, for example. So in this panel here, I'm plotting the stellar mass of the host galaxies, like a probability distribution of the host galaxies for different values of the alpha common number, alpha equal to 1, 3, and 5. We can do that because doing this process is fast, so we can change our population of compact objects. Color-coded are different redshifts. The color code is always the same. Dashed line is the property of the formation galaxy, and solid line is the property of the host galaxy. So if you focus in this area here, you see that black holes tend to form in low-mass galaxies and tend to merge in low-mass galaxies. Because if you remember, with alpha equal to 1, you have short delay times. Then low-mass galaxies are like a good place to the formation and merger of black holes because they are metal poor. So you expect that basically your black hole forms and merge almost in the same galaxy with like little differences. If you instead use, for example, alpha equal to 5, you see that they still form in low-mass galaxies, where is the place that you expect them to form because they are like metal-poor galaxies, but they tend to merge in high-mass galaxies. Basically, the distribution here is shifted to high-mass galaxies. And this happens because this is an effect of the common envelope. So alpha equal to 5 gives you back longer delay times, so your formation galaxies has more time to evolve and to become like a more massive galaxies. We can see again this trick if you look at the distribution of passive galaxies. So passive galaxies are galaxies with like a poor or zero star formation rate. We can model them in Cosmology because we have the galaxy stellar mass function. So in general, the number of passive galaxies is increasing with as you approach to the local universe. So here is like high redshift 2 if I'm wrong, yeah, redshift 2, redshift 0. This dashed line here is the number of passive galaxies, which is increasing in the local universe. This is like how your universe work. The lines are the number of mergers, total number of mergers in passive galaxies, which is also increasing. So basically, this is, for example, what is happening in GW17-817. We observed the BNS merged in a passive galaxy, and the number of merging in passive galaxies is increasing as we approach the local universe. GW17-817 is very close to us. But also, you can see again the effect of delay time, especially in the case of BBHs. In the case of BBHs, you see that the total number of mergers in passive galaxies is different as you select different delay times. For example, if you get like alpha equal to 5, so longer delay times, you expect your host galaxies to be, so you have higher chances that your host galaxy to be passive. Again, because with longer delay time, you let your formation galaxy more time to evolve, and probabilistically, it is going to be a passive galaxy if it is approaches the local universe. Okay, can host galaxy be used in other ways, other than ranking or just modeling them? Of course, yes. Because gravitational waves are standard sirens. What does it mean? It means that in the amplitude of a gravitational wave, it is encoded the luminosity distance. And luminosity distance is a parameter that we can extract from gravitational waves. And this is very, very important and very unique also. You can also extract the redshift at which the corresponding luminosity distance, but to do so, you need to fix a cosmology, of course. So we can try to constrain the redshift in other ways, and what we can do is to constrain the cosmological parameters. And this is what we do. For example, what we did with GW17-817 was to estimate in an independent way the Hubble constant. So since we had the host galaxy, we could measure the recession velocity. From the gravitational wave parameter estimation, we get the luminosity distance. You put your number in, and you get like an independent estimate of the of H naught. However, it has like a huge uncertainty. Here I'm plotting that. So H naught is a function of the inclination angle. Do you remember why the inclination angle? Say it. So the inclination angle is degenerate with the luminosity distance. It's going to be clear. Other estimate of the H naught, of course, are providing you like tighter constraints. This is like a huge uncertainty corresponding to them. But the problem is that we just have one host galaxy, so the statistic is low. And you can do cosmology with gravitational wave in two ways. The first one is with bright sirens, the example that I just showed you. Bright sirens means that you know the host galaxies because you have electromagnetic counterpart. In the case of GW17-817, we had the kilonova, so we were able to pick the host galaxy, so we were able to actually measure the redshift or the recession velocity. So bright sirens means when you have the electromagnetic counterpart. And this is what I was telling you about the distance and inclination angle degeneracy. So you see this banana shape here. This is the parameter estimation coming from the gravitational wave detection. You could, let me go back to one slide. So if you have some ways to constrain the inclination angle, so like slicing this 2D probability distribution, you can constrain better the H naught. This is the logic. So go back again. Basically, we can do that with models, for example, of the kilonova or afterglow model. Because we can model the kilonova. This is basically the first slide I showed you before. Based on the luminosity of the kilonova, we can estimate the inclination angle, and so we can better constrain the luminosity distance and consequently the H naught. The other way of doing cosmology is with dark science. It means that you do not have the electromagnetic counterpart, but still you can use the information coming from catalogs and parameter estimation from gravitational waves. What you do is you cross-correlate with all the galaxies that are enclosed in the volume coming from gravitational wave observation. Ideally, the two methods would be the same if your sky localization is perfect, so it detects just one host galaxy. You would have exactly the same result. This is not the case, of course, because what I'm plotting here is the sky localization of GW17-0817 with highlighted NGC 4993. These are all the galaxies that are in the sky localization from GW17-0817. So you can potentially, so this is like another way to do cosmology. Of course, it is proportional, trivially is proportional to the sky localization. So what did you learn today, hopefully? So we talked about multi-messenger astrophysics and the host galaxies, and how we can model them, both with cosmological simulation and with like a fast approach, like galaxy rate. And this can be used for example, to cosmology. Tomorrow, last lecture, we are going to see population synthesis, like closer, where I'm going to present you like an example of population synthesis. We're going to talk about population 3 stars and black holes. This is going to be like the perfect excuse to introduce you the Einstein telescope and the future of gravitational waves. I let you with further reading, as I did like the other times. If you're curious about the chemical evolution of the universe, this is like a super nice review, where I also took some of the plots I showed you. If you want to know more about dark science, I'm leaving you with a bunch of references. I think it's lunchtime.
We are taking the school picture right after the question, so don't leave straight away for lunch. Questions now? Where is the second microphone? Okay, good. So you do that side.
Filippo, what's the definition of the inclination angle? Is 0 when you're watching the jet
Face on.
In your direction, and 90 degrees in the looking edge on, right?
So it's the angle between the angular momentum of the binary and your line of sight. So if the binary is looking at you, the inclination angle is 0 or 180 degrees. It's 90 degrees where it's perfectly perpendicular.
Perfectly?
Perpendicular.
Okay. And could you show that that slide with brighter shining bright? Yes. What's the meaning of hydrojet curves?
I have no idea. I'm sorry.
Okay.
I would look at the reference. I cannot tell you. I'm sorry.
But some kind of constraint of.
Yeah, here the idea is to put constraints on the inclination angle, because as you see, it goes basically from 0 to 60 degrees. What you can do with you can take advantage of the models that we have on kilonova and afterglow emission to constrain the inclination angle. So these are, for example, the two cases with so LBI plus LC is the kilonova and afterglow emission. If you sum, you can the sum with gravitational wave is the blue line here that actually is constraining the luminosity. So if you do not know the inclination angle, the uncertainty of non-luminosity distance is the integral of this 2D distribution.
So when we use dark sirens, especially when we use galaxy catalogs, one step in the process is to assign a probability to each host galaxy, to each potential galaxy as a host. And I've seen, normally people weigh by their mass or by a tracer of their star formation rate. So, but like with the content of your lecture today, can we like make more informative weights?
Yeah, potentially, I would. It is like a project that I think is interesting to look at. Is evaluating the ranking probability with galaxy rate. Because usually, as you said, they use like a tracer of the mass or star formation rate. But unfortunately, you are not taking into account all the uncertainties that you have, specifically on compact object formation. So it would be nice. I didn't do that, but it would be nice to, as a follow-up, to do exactly this, to rank galaxy, also taking account these uncertainties.
And just unrelated question, I don't know if you're going to talk about this tomorrow, but what do third generation detectors change in our knowledge about, what will they change in our knowledge about?
Yeah, so there is like a super vast literature on, I can send you like a reference. No, I'm gonna give you the reference in the slides of tomorrow. But this is like one of the key scientific goal of the Einstein telescope, for example, because Einstein telescope is in itself like a 3 detector. So by itself is going to give you like quite good sky localization. If you combine it with current gravitational wave detectors or future other gravitational wave detectors, sky localization is going to improve a lot. And there are several works that show how you can the constraint that you can have on H0 by using third generation detectors, which is going to improve it like on the % level.
And in terms of what we know about the host galaxies? Because I mean, we will expect more events like GW17.
Sure. Yeah, absolutely, yes. To boost multi-messenger astrophysics, you need third generation detectors that are going to give you like good sky localization, but also you need other electromagnetic facility as Vera Rubin, because actually detecting a kilonova is not that easy. It's a faint emission that can be outshined by the afterglow, so you want to be sure to catch it. Again, I'm going to give you tomorrow like a reference that showed you the numbers of host galaxies that are going to be detected. It's a forecast, of course. The host galaxies are going to be detected with third generation detectors, yes.
Going for the picture one. Going twice. Okay. Let's thank Filippo again. And we'll go for the picture.